Polynomial and Rational Inequalities. You should be familiar with graphing polynomial and rational functions. You should also be familiar with interval notation. In this lesson, we will solve inequalities involving polynomial and rational functions. Recall the steps to analyze the graph of a rational function. In particular, we divided the number line at the x-intercepts, which occur when the numerator is 0, at the vertical asymptotes, which occur when the denominator is 0, then determined on which intervals the function was positive and negative. It was easiest to do this when the function was written in factored form. Here is an example of a polynomial inequality. First, we divide the number line where the expression on the left of the inequality equals 0. We can then examine on which intervals the function is positive and negative. To the right of 3, both factors are positive, so the function is positive. Between -4 and 3, the factor x plus 4 stays positive, but the factor x minus 3 becomes negative. Altogether, the expression on the left is negative. To the left of -4, both factors are negative, and the expression on the left is positive. If we expand the expression on the left, it will be a polynomial that begins with x squared. This confirms our analysis. It is a parabola that opens upward. The function is greater than or equal to 0 when x is less than or equal to -4 and when x is greater than or equal to 3, which we can write in interval notation. Here is a similar example with exponents. First, we divide the number line where f of x equals 0. To the right of 3, both factors are positive, so the function is positive. Between -4 and 3, the factor x plus 4 stays positive. We cross past 3 for a factor with an even exponent, so we stay on the same side. The x minus 3 factor is a negative squared, and so remains positive. To the left of -4, the cubed factor changes sign. Since it's an odd power, the graph will cross the axis to the negative side. If we expand f of x, it will be a polynomial that begins x to the 5th. This confirms our analysis. An odd power of x begins on the negative side to the left and ends on the positive side at the right. The function is less than 0 on the intervals when the function is negative, that is, when x is less than -4. We also need to include the points where the function equals 0. In other words, we include the points -4 and 3. The solution is the interval x is less than or equal to -4 plus the single point 3. Here is an example where we need to simplify first. This technique only works when we are comparing a function to 0, so that we can analyze when the function is positive and negative. Therefore, our first step is to make one side of the inequality 0, then write the function in factored form. We split the number line at the x-intercepts and analyze the factors. The function is negative between -2 and 3. In this case, we are strictly less than 0, so we do not include the endpoints. Here is the original example of a rational function. It is already in factored form. We place the x-intercepts and the vertical asymptotes. Note that the function equals 0 at the x-intercepts, so we will include these points, but the function is undefined at the vertical asymptotes, so we will never include those points. Then we analyze where the function is positive and negative. We find 4 intervals where the function is positive. We also want to include points where the function is equal to 0. The function is undefined when x equals -1 and when x equals 1, so we cannot include those points. The function equals 0 when x equals -3 and 2, so we should include those points. The rightmost two intervals can be joined since they share an endpoint. To recap, to solve an inequality involving a rational function, first make sure that one side equals 0 and that the rational expression is factored. Then analyze the number line by placing x-intercepts, vertical asymptotes, and deciding where each factor is positive and negative. If the inequality is strictly less than or greater than, then the endpoints will not be included. If the inequality is greater than or equal to, or less than or equal to, then the x-intercepts will be included in the intervals. The x-values of the vertical asymptotes are never included since the function is undefined at these points. If two adjacent intervals share an endpoint, they can be combined into a single interval.